Yesterday we completed what we want to cover for lecture 7. Okay, lecture 8 is on communication systems, which I will leave for the class on communication system. Okay, so we'll go on, skip over to chapter 9, which talks about the Laplace transform. Okay, so the Laplace transform you can think of as the generalization of the Fourier transform for continuous time signals. Okay, so since assuming you understand what is the Fourier transform, it should not be difficult to extend to this Laplace transform case. Then in chapter 10, we will have the Z transform, which is an extension of the discrete time Fourier transform, a generalization of the discrete time transform, similar to what we do in chapter 9. Okay, so chapter 9 and 10 are quite similar. Okay, so let's start. Let's see how this is a generalization of the Fourier transform. Okay, so if you recall, one of the main motivations for studying the Fourier transform is because when we look at a linear time invariant system, we know that a complex exponential, e to the st, right, e to the power st, is the eigenfunction to any linear time invariant system. Okay, so a complex exponential, e to the power st, is the eigenfunction to any linear time invariant system. So this means that if you input e to the power st into this linear time invariant system, right? So if you take the convolution between e to the st and this impulse response h of t, you will see that the output will give you the same complex exponential, just scaled by some value that depends on s. Okay? So this is one of the main motivations for studying Fourier transform, because now if we are able to write a input signal as a linear combination of these complex exponentials, then the output should also be a linear combination of the same complex exponentials. Okay. Now previously we focused specifically on the case where s is a pure imaginary number, right? We focused on a case where s is equal to j omega, right? But actually, this statement holds in general, right? So this e to the st is an eigenfunction of any linear time invariant system. This holds for any value of s, okay? So this statement here holds for any value of s. All right. So again, saying that this is an eigenfunction of the linear time invariant system means that if you insert this into the system, your output will also get the same complex exponential scaled by some value, capital H of s. Okay? And it just so happens that this capital H of s is the integral of h of tau times e to the minus s tau. All right? Now, if s is j omega, then what we have is exactly the Fourier transform, right? So if s is j omega, then this is the Fourier transform of h of t, okay? Now, if s is not necessarily j omega, but any arbitrary complex number, then what we have is the Laplace transform, okay? So the Laplace transform is just a generalization of the Fourier transform for arbitrary s, right, rather than just j omega, okay? Right, so are we good? Okay, all right. So how can this be useful, right? Why do we want to generalize the Fourier transform, right, for an s that is equal to j omega to some arbitrary complex number s, right? What's the advantage of doing that? Okay. Now, all right. Now, suppose this is the Laplace transform that we want to look at. Okay. So to simplify our notations, right? We describe this relationship between x of t and capital X of s with this calligraphic L. Okay. So if it's an f here, then we have the Fourier transform. If it's an L, then this is the Laplace transform. Okay. Now, if you assume that s, right? S can be any complex number, right? Now, suppose that you write s as sigma plus j omega. Okay. So you just plug s as sigma plus j omega inside here. Then the Laplace transform x of s you can write as x of sigma plus j omega, which is the integral of x of t times e to the minus sigma plus j omega t. Now, if you just group this e to the minus sigma t together with x of t, then you get something like this. And what is this? This is simply the Fourier transform of x of t times e to the minus sigma t. Okay? So what is the Laplace transform? The Laplace transform is actually just a Fourier transform, but now with your signal of interest multiplied by this exponential. Okay? And what's the advantage of doing that? Right? So suppose that you have some signal x of t that looks like this. Okay? So suppose your x of t looks something like this. Okay? So if you recall, for x of t to have a Fourier transform, by Dirichlet condition, x of t must be absolutely integrable. Okay? So for this Fourier transform to hold, this x of t must be absolutely integrable. All right? But if you have a function x of t that continues to grow unbounded as t goes to infinity, then this function cannot be absolutely integrable. Okay? So if you're looking at a function that looks like this, the Fourier transform does not exist. Right? We cannot find a Fourier transform for this. Right? But, I'm sorry? 忽然领悟到了吗 ？OK， 那你说说看好了。对，没有，我觉得不错啊，对啊，对对对，厉害厉害，所以这个人生的体悟都很感人，对不对？对，所以就是说。它这个本来是 unbounded 就会一直成长，所以你没有办法是 absolutely integrable。但是现在透过乘上 e to the minus sigma t, right? You can sort of suppress the growth of this signal on the right-hand side to make it integrable. Okay? So you can multiply this signal. If you multiply this signal with a decaying exponential like this. Right, so suppose that this is e to the minus sigma t. Okay. Then by choosing sigma large enough, right? By choosing sigma large enough such that it decays, suppresses this enough, this thing can become absolutely integrable. Okay? So it's possible to make this absolutely integrable. Okay? So even though in certain cases where x of t by itself is not absolutely integrable, if when multiplied by this exponential makes it absolutely integrable, then we have the Laplace transform. So even though the Fourier transform does not exist, we can analyze it using the Laplace transform. Okay, so this is the main advantage of the Laplace transform. Right. Okay, so a note here, the Laplace transform can be used to analyze signals or systems that are not absolutely integrable. Okay? And for systems that have impulse response that are not absolutely integrable, you're basically saying that the systems are unstable, right? Or unstable. Okay. So that's about it, right? So to understand Laplace transform, I think the key point to understand is that the Laplace transform is actually just the Fourier transform of your function times this exponential, decaying exponential, okay? So here sigma can be either positive or negative, right? If it's positive, then it suppresses the right-hand side of the signal. Right? If it's negative, then you can make it suppress the left-hand side of the signal, okay? So, depending on what your original x of t would look like, you would need to choose an appropriate value of sigma in order to make it, to suppress either the right side or the left side more, okay? Okay. All right, so let's look at a few examples. Okay. All right, so suppose we consider the case where x of t is e to the minus at u of t. All right, so this is a right-sided signal, all right? It's non-zero only on the right side of the origin. This could either be a decreasing or increasing exponential depending on whether a is greater than 0 or less than 0, okay? But let's suppose we start out with the case where a is greater than 0, okay? So suppose that a is greater than 0, okay? Then suppose you take the Fourier transform. So this gives you x of j omega summation integral e to the minus at u of t e to the minus j omega t. This u of t limits the integral from 0 to infinity. And the integral 0 to infinity of e to the minus at times e to the minus j omega t gives you simply 1 over j omega plus a. Okay, so we've done this several times in the previous chapters, right? So this is the Fourier transform. Now, what about the Laplace transform? Okay. Right, so the Laplace transform, right, by definition is just this x of s, right, equal to integral e to the minus at e to the minus st dt, right? I should limit this from 0 to infinity, because of the unit step function, okay? Or, by letting s be equal to sigma plus j omega, you can view x of sigma plus j omega as the integral 0 to infinity e to the minus at e to the minus sigma plus j omega t dt. Okay? And if you group together at and sigma t, right, the real parts of the exponent, you get e to the minus a plus sigma t times e to the minus j omega t dt. Okay? All right, so as I mentioned before, the Laplace transform is simply the Fourier transform of the original signal e to the minus at times the decaying exponential e to the minus sigma t. Okay, so we're just looking at the Fourier transform of this. And we know what this looks like, right? We know what the Fourier transform of this looks like. It's basically this with a plus sigma here. Okay. Okay, so this is 1 over j omega plus a plus sigma. Okay? But for this to be true, a plus sigma must be greater than 0. Right? Okay. So we're looking at the Fourier transform of this e to the minus a plus sigma times t. So in order for this to have a Fourier transform, a plus sigma must be greater than 0 so that this is a decaying exponential. If a plus sigma is less than 0, right? If this is less or equal to 0, then this would be an increasing exponential that is not absolutely integrable and would not have a Fourier transform. Okay? So for this Fourier transform, for the Fourier transform of this to exist, a plus sigma must be greater than 0. Okay? So in other words, the Laplace transform for this function here exists only if, a plus, the real part of s, is greater than 0. Okay? So hence, the Laplace transform is x of s equal to 1 over s plus a, right? Because s is sigma plus j omega, I combine it into an s. And this holds only if the real part of s plus a is greater than 0, okay? Or if the real part of s is greater than minus a, right? Since a is already real by the premise of the problem. Okay? So the Laplace transform of this decaying exponential is 1 over s plus a when the real part of s is greater than minus a. Okay? Now notice that the Fourier transform can exist only when a is greater than 0. But actually, if you look at the Laplace transform can exist even when a is not greater than 0, right? If a is, let's say, some negative number, then minus a is positive, then I simply need to choose an s with a real part greater than minus a, right? And I still can find the Laplace transform, okay? So even if this signal is increasing exponentially, right, I can still find a large enough S, right, that suppresses it on the right-hand side to give me the Laplace transform. Okay. All right, so in conclusion, what this tells us is that this signal here, e to the minus at times u of t, has a Laplace transform that is 1 over s plus a. But other than this, you must also specify when this exists, okay? You must specify when this integration exists. And this exists when the real part of s is greater than minus a, okay? So this condition here we call the region of convergence, okay? Or the ROC for short. Okay. So when specifying the Laplace transform, you not only need to specify the algebraic expression, you also need to specify what is the region of convergence. Okay. So like I just mentioned, right, the Fourier transform does not exist for a less than 0, but the Laplace transform does by choosing an S that is large enough. Okay. Okay. Now, if you think about it, the Fourier transform is actually just a special case of the Laplace transform with sigma equal to 0, right? So the Fourier transform is just a special case of the Laplace transform with the real part of S equal to 0. Okay. Now, if A is greater than 0, then the region of convergence will include all values of S for which the real part of S is greater than minus A. Okay? So when A is greater than 0, then this 0 value is greater than minus A. And therefore, the Fourier transform lies within the region of convergence of the Laplace transform, meaning that the Fourier transform should exist. Okay? But if A is less than 0, then minus A is positive. Okay? So the region of convergence would include values of S that should be greater than some positive value. But since the Fourier transform corresponds to a value of S that has a real part equal to 0, it does not lie in the region of convergence when A is less than 0, and therefore it would not exist. Okay? All right. Now let's look at a similar example. Okay. So in this example here, we have a right-sided exponential, right? Either decreasing or increasing, depending on whether A is positive or negative.